look down here at this first atom. This is manganese. It has 25 protons, so therefore it has 25 electrons. If I go in there and I remove the most loosely held electron, what is left when that electron leaves? Well, I would have a manganese ion, so it'd be positively charged. And recall what happens to the size of a cation? Well, when that electron leaves, the nucleus is going to pull in that electron cloud tighter. So a cation is always smaller than its neutral atom. So to go in and remove a second electron is going to take even more energy, because recall Coulomb's law. So the closer it is, the attractive forces are higher. And so to remove a second electron from what is a cation, it's going to take even more energy. So the energy per atom should go up and up and up. And we should see the difference between p electrons and s electrons. Again, s electrons are harder to remove, p electrons are easier to remove. So every single electron of every atom we could rip off. So kind of maybe a form of chemistry torture. So let's look at aluminum and let's take off an electron one at a time from the atom. So let's start with this first picture here. So we have aluminum. It has 3 valence electrons. So when you look on the periodic table, so recall that your noble gases have 8 valence electrons, and then you count down 8, 7, 6, 5, 4, 3, and then I should have 2, and there's hydrogen 1. So these are the valence electrons. So we find aluminum in the boron family with 3 valence electrons, and they're drawn here in the diagram. So 3 outer electrons. Let's go and remove 1 electron. And you're not expected to memorize the energies, but I did look this up. And to remove that 1 electron, the most loosely held electron, we find that it takes 577 kilojoules of energy to remove that electron. And when that happens, I now have an aluminum ion. So it's a cation. So the electron cloud would be even smaller. And let's go and remove a second electron. And so when I remove that electron, I looked up the value for this, and it happens to be 1,810 kilojoules to do this. So notice that it's even more energy to remove 1 more electron. So the energy goes up as we go atom by atom. Let's remove a third one. And again, I looked this value up. So this would be removing from an aluminum 2 plus ion. This would take 2,750 kilojoules of energy to remove this. And what's left is an aluminum 3 plus ion. Now notice what's left. So all the valence electrons have been pulled off, and all I have left are those core electrons. I can count that there's 8 valence electrons right now in that aluminum 3 plus atom. Well, let's go ahead and remove 1 more electron. So I'm going to remove 1 more electron, and it's from a noble gas configuration. So right now it's just like a noble gas, but to go in and remove 1 more electron, one of the core electrons, I looked up how much energy this would take, and this would take 11,580 kilojoules. That's a lot of energy. And in a normal chemical reaction, there's not enough energy to remove that 4th electron. So in aluminum, in a normal reaction, you can remove the 3 valence electrons, but no more. So it's like there's a barrier or a wall here. So I'm going to attempt to draw a wall here. So here's my wall. This is my energy wall. There's not enough energy to remove that 4th electron. Or you could look at it like there's a big stop sign. So you can remove 1, 2, 3, but then there is not enough energy to remove that 1 more electron. So it will remain this noble gas configuration with the 8 electrons. We can look at a table of ionization energies for each element. Let's look at just a few of these. Let's look at carbon. Can you see where the big jump is? The jump between the valence electrons and those core electrons. So let's look at carbon and let's figure out what's going on. So the first energy, or the first ionization energy, the first electron to take off is about 1,000. And then we have a second, that one is about 2,000. And now we have a little jump here with the 4,600 about. So it does jump up a little bit here. Are there any more big jumps here? Let's keep going. About 6,000. And then we have 37,000. That's a lot. It's like this is a stop sign. There is not enough energy to remove more than 4 electrons in carbon. Now, if you look at carbon, how many valence electrons does carbon have? Well, it has 4. So it's in the group number 4A. And so that 4, that Roman numeral 4, that is telling you how many valence electrons there is. So we have our core electrons over here on this side, and then we have our valence electrons over here. So again, there's not enough energy to remove those core electrons. So carbon can lose 4 valence electrons, and then that's it. Now let's explain these little jumps. So if you look at carbon, carbon ends in P2 as its electron configuration. So it'll end in 2p2. So when you go and remove those electrons, we find that you first remove a p electron, and then another p electron, and then the next 2 electrons are s electrons. So recall that we have talked about before that s electrons take more energy to remove than p electrons. So that's why you see these little jumps, and then you'll see a bigger jump when you remove those core electrons. So let's look at one more element here. Let's look at lithium. So looking at lithium, can you find where the big jump is? So we go from about 500 to 7,000. That's a pretty big jump. That's a jump by about 7,000-ish. And then there's another jump here, this time from 7,000 to 11,000. So maybe about a jump of about 4,000. So where's your big jump? Well, it's that jump of almost 7,000. So this right here is the wall, or the stop sign. So how many valence electrons does lithium have? It has 1. So these right here are the core electrons over here on the right hand side, and then we have our 1 valence electron with lithium. So we can see where that big jump is. If you try to remove a core electron, again, it will just take too much energy, and that will be an energy barrier, so that when lithium goes and reacts, it can only lose 1 electron, and then that's it. So just to review, we have large jumps at energy level changes. So when those valence electrons are lost and you go down to the next energy level, to remove an electron from that inner level is going to take a lot of energy. Smaller jumps at sublevel changes. So again, that's the difference between S and P electrons. S electrons take more energy than P electrons. In chemical reactions, only the outer valence electrons are affected. So again, there's not enough energy to remove those inner electrons. The ease of which electrons are removed is related to those the oxidation numbers that we've talked about. So remember the oxidation number pattern. So group 1 has a +1 charge, group 2 has a +2. Your boron family has +3, nitrogen or carbon family has +4, and then the nitrogen family is where it starts negative. So nitrogen family -3, oxygen family -2. The halogens are -1, and your noble gases do not have oxidation numbers. All right, so here I have 3 mystery elements. I'm going to do the first one, and I want you to try mystery element Y and Z. I want you to try to guess how many valence electrons it has based on this ionization data, and it's just removing 1 electron at a time. So first electron, second electron, third electron, fourth, fifth, and sixth, and I just have them listed up and down instead of across left to right. So let's look at element X. So let's look up for the big jump, and we see we have 700, 1500, 3000, 4000, 16,000. That's a big jump right there. So this is my barrier right there. So I know that this has 4 valence electrons. Well, looking on the periodic table, what family has 4 valence electrons? That's right, this is the carbon family. The carbon family has what oxidation number? A +4. The reason why it has a +4 is because of those 4 valence electrons. When they're lost, you end up with a charge of +4. And what would the electron configuration end in? Well, the carbon family ends in P2 because you can count those electrons. P1 for the boron family, P2 for the carbon family. So valence electrons would end in P2. If you had to make up one, like a sample, maybe possible electron configuration, you could do 1s2, 2s2, 2p2. The important part, though, that it does end in p2 because that's the carbon family. So go ahead and stop the tape and do Y and Z, and then we'll come back and do the answers. Okay, so for element Y, you should find that the big jump is right here. So you go from about 3,000 to 25,000, so that's a really large jump. So this has 3 valence electrons. So looking on the periodic table, the family that has 3 valence electrons is the boron family. Boron family has a +3 oxidation number, so that will be the charge of an atom when these 3 valence electrons are lost. And it will end in P1. So you could do a sample electron configuration, 1s2, 2s2, 2p1. Let's look at the last one, element Z. Let's look for the big jump. We have a jump between after the first electron, after when it's lost, it jumps up by about almost 3,000. And so this is where that barrier will be, the energy barrier. So I have 1 valence electron. What family has 1 valence electron? That would be the alkali metal family. The alkali metal family has a +1 oxidation number, and it ends in S1. Let's go back to a previous unit where we talked about PES diagrams, and I have the same element here but just drawn 2 different ways. So in this bottom way, they drew it backwards with high energy first, so we can do the electron configuration in order. Remember, it always starts with 1s2, 2s2, so we can measure the height. The height is always starts with 2. And then we can see this one, it goes up by 6, so 2p6 is the pattern, and then 3s2. And we know it's magnesium. This other one here, we just have to write it backwards, so 1s2, 2s2, 2p6, and then 3s2. You can see the jump in energy. So here it's almost 1, and this is your valence electron. All the rest are core electrons. So you can see quite a large jump between about 1 and then it jumps all the way to 5. So again, these are your core electrons, these other ones. So to look at this, here is your valence electrons, and then these others, these are your core electrons. So the closer you are to the nucleus, the more tighter a pull on those electrons, the nucleus will have more of a pull on those electrons, those core electrons. Here's some more practice if you're interested. So go ahead and stop the video and answer this, and then we'll come back. All right, so we're back. Let's look for the big jumps. So element X this time, the big jump is right after removing the second electron. So this will have 2 valence electrons. And looking on the periodic table, this is an alkaline earth metal. Oxidation numbers for alkaline earth metal would be a +2, and it will end in an S2. Looking at mystery element Y, we're going to look for the large jump. I think the largest jump is probably this first one because it jumps about 4,000. And so this is going to be an alkali metal. And alkali metals, they have oxidation number of +1. They end in an S1, and they have 1 valence electron, so it's just right there. Let's look at that last one, looking for that big jump. It would be right here. So that is 1, 2, 3, 4 valence electrons. So this would be the carbon family. The carbon family, it ends in P2 and has oxidation number of +4.